Hello everyone. Today we are going to start lecture 5, that is on microwave remote sensing 1, right. So, like previous lectures, this lecture is also divided into two parts. This is the second lecture of second module and fifth lecture of this particular course, right. So, you remember this slide where we have mentioned different domains of remote sensing, the reflection, emission and then microwave, right. So, here what do we measure? Here we measure the back scattered energy. Right, and you see here we have incoming radiation from the sun as well as incoming from the sensor. So, this is possible that we can have active as well as passive microwave remote sensing for any given target, right. So, this is active and passive, this is just an example. Now, we have to think about role of the atmosphere here, what kind of depth of penetration we will have, and then what information we will have which is not possible with reflective and emissive domain, right. So, the role of atmosphere, since we are talking about the scattering and the absorption, remember the scattering, it is more influencing in the shorter wavelength because we are talking about the size of the scatter and the wavelength. If the size of the scatter is equal to the wavelength, we have scattering. If the molecule is larger than the wavelength, it is having the scattering phenomena. But since we are talking about this microwave which is 0.1 centimeter to 1 meter, this is longer wavelength region. So, in the longer wavelength region, the scattering effect will be very less or negligible, right. That is the reason we can use microwave remote sensing when we have cloudy days, when the atmosphere is having the aerosol dust particle. In such situation also you will have microwave remote sensing data. So, if this is the situation for the higher altitude areas where the sky is almost always cloudy. So, in such situation microwave remote sensing is more useful. And remember I talked about the depth of penetration in visible, NIR and the thermal infrared also, and I mentioned that depth of penetration is equal to the wavelength, right. So, here we are talking about the microwave which is 0.1 centimeter to 1 meter. So, the depth of penetration will be more here compared to your optical remote sensing, because these two is known as optical remote sensing. This is microwave. In microwave remote sensing you have more depth of penetration, whereas the emission, it is not following the depth of penetration of the light, it is the volumetric property, right. Now, what different information we will have from microwave remote sensing? Since here we are having the depth of penetration better than the optical remote sensing or the reflective domain, we will have the subsurface information, right. That is point number 1. Then second point is, here we will have very little information about the composition of the target, whereas we will have more information about the structure of the target. So, this particular slide I made to explain or to remind you about the Rayleigh scattering, Mie scattering, non-selective scattering. Now, here you see in non-selective the size of the scatter is greater than the wavelength. Here in the Mie scattering, it is as good as your wavelength, and when we have the Rayleigh scattering, we have wavelength larger than the size of the scatterer, right. If you look here, the advantages of microwave remote sensing. So, here it says Microwave radiation can penetrate through the cloud cover, haze, dust and all but the heaviest rainfall, right. Not vulnerable to atmospheric scattering like shorter optical wavelength. That I explained you already, that since we are talking about the size of the scatterer, which is equal to or less than or greater than the wavelength, this microwave remote sensing 0.1 centimeter to 1 meter, that will not have much problem because of this scattering. So, atmosphere is clear for us, at least for this longer wavelength, right. And because of this, we can do the remote sensing in the cloud cover, haze, dust and all but the heaviest rainfall, because that time the signal or the energy which is back scattered from the surface will be interacting with your water, right. So, because of that it is very difficult. Now, the disadvantages. So, the disadvantage says very costly instrument setup, right. So, here this compared to optical remote sensing, this is costlier. Then the output of microwave remote sensing is complex and hard to interpret, because earlier we talked about the optical remote sensing output where we had only the pixel. The pixel will have x, y and z values. X is your latitude, y is your longitude and z is your dn value. And these dn values were further converted to radians and then further converted to reflectance, right. But here when we talk about the microwave remote sensing output, it is in the complex form A plus IB, right. So, this is not the simple dn value. We will understand this in subsequent slides. Very little information related to the composition of the material, that I already mentioned, that in microwave remote sensing we have different type of information rather only looking for the composition. If you are interested for composition, you should go for optical remote sensing. But if you are bother about the subsurface information or soil moisture kind of information, then you are supposed to use this microwave remote sensing data. This particular slide will explain you the active microwave remote sensing, where the sensor itself has a source of light in the microwave domain. So, this is 0.1 centimeter to 1 meter, right. So, in this domain we have a source which is available with this particular satellite, and this is illuminating the surface. You can see how the pulses are sent and then it is reaching to the ground, right. So, once it is interacting with the ground, what will happen? The reflection will take place, the back scattering, and then this back scattering will slowly reach to the sensor, right. And then we will capture how much time it has taken and what is the back scattering value. Right. So, these two things will be measured and this will be recorded for a particular pixel. In this slide, here you see there is one microwave remote sensing instrument which is available with this particular airborne flight, and this is illuminating the surface, right. Now, see it very carefully. Here the pulses are sent. Now, the pulses will interact with different target available in this field of view, right. Now, this particular tree has interacted first, you see it has interacted first. So, what will happen? This will provide the back scattering value before this house here, right. So, you see this has started giving the back scattering signal. So, it is slowly it is reaching to this particular sensor, and then next this backscattering signal of this house will reach to this sensor, right. So, what is happening? This particular object, in this case it is a tree. So, this tree will provide the backscattering signal before this. So, time will be less for this, right, and here it will show the time delay, right. Based on that, the objects will be identified, which is near, which is close, which is high, which is low. That kind of information can be measured with this data. In case of passive remote sensing, so here the sun is our source, which is illuminating the whole area together, and then the signal is going back to the space, and then it is getting measured by the passive microwave sensors, right. So, this is called active or backscattering radar. This is called passive. Here it is, we are using the radiation or the passive radiometers, right. So, if you see here, this particular graph, it shows the wavelength versus percent transmission one way. So, this is transmission in our atmosphere. When we have water clouds or ice clouds, the percent transmission is almost very good, right. When we have wavelength and the percent transmission here again in the percent, and here you can see how it is behaving, right. So, when we are increasing the wavelength, this percent transmission is also increasing. That means, the moment we are increasing the wavelength, transmission is increasing, right. So, because of that, the water cloud or ice clouds, they are not the biggest problem during this measurement. So, that is why microwave remote sensing is very suitable for higher altitude areas where you have more cloud cover over the year, right. The amount intensity of emitted, reflected or transmitted microwave energies are very small, which is generally insufficient for the passive microwave sensor or detector, right. So, remember this E is equal to SC by lambda. So, here what is the relation? This is E energy and this is wavelength, right. So, if the wavelength is low, energy is high, right, and if the wavelength is longer, energy will be low. And since we are talking about the wavelength in the order of 0.1 centimeter to 1 meter, the wavelength is too high, right. So, energy will be very, very less, right. The amount intensity of the emitted microwave energy is related to the temperature and moisture properties, because we are talking about this wavelength which is absorbed by the surface which is having the moisture condition, right. So, microwave energies are absorbed or it will be eaten by the surface if they have high moisture content, right. So, in this situation what will happen? This will be controlled by the surface property. Since the microwave wavelengths are long, the energy available to passive sensor is very low. When we rely on the sun as our source of light, right. So, naturally this is illuminating this particular target and it is getting reflected. So, in that condition we are following this fundamental, and here the longer the wavelength, energy is low. Because of that, the energy which is released from the surface will be very little to be resolved by our sensor. So, what do we do that time? We increase the spatial resolution or we increase the size of the pixel. So, then you have bigger pixel. So, that is why this passive microwave sensors are characterized by low spatial resolution. I hope this is clear. The energy and the wavelength relation that is being used here to decide which particular size will be suitable for the microwave remote sensing. Now, we will talk about the application of passive microwave remote sensing. The application of passive microwave remote sensing include meteorology, hydrology and oceanography. So, in these areas, microwave remote sensing data sets are widely used. Meteorologists can use passive microwaves to measure atmospheric profiles and to determine water and ozone content in the atmosphere, right. Hydrologist uses passive microwaves to measure soil moisture, since microwave emission is significantly influenced by moisture content. So, what happens if you have a surface which is moist or it is having the moisture content? The dielectric property of this particular surface will control how much amount of energy will be absorbed in the microwave domain, right. So, that is why microwave remote sensing can be used and are widely used for moisture related studies. Oceanographic application include mapping sea ice, currents and surface wind, as well as detection of the pollutants such as oil slicks in the ocean, right. These are some of the applications where microwave remote sensing is widely used. Active microwave sensors provide their own source of microwave radiation to illuminate the target. Remember the previous slide where I have shown you two examples, one where sun is the source of light and in another case the sensor itself has the source of radiation. The active microwave sensors are generally divided into two distinct categories. The first one is imaging and another one is non-imaging. So, this is also true for the other remote sensing, right. So, either we can generate an image or we can have only point measurement with the help of ground instruments, right, which is looking at a particular area, and for this particular pixel only you are getting all these values, right. So, similarly in the microwave domain we also have this imaging and non-imaging, and for non-imaging some examples are altimeters and scatterometers. The most common form of imaging active microwave sensor is radar. This is very popular, right. Radar is an acronym for radio detection and ranging, which essentially characterizes the function and operation of a radar sensor. The sensor transmits a microwave radio signal towards the target and detects the backscattered portion of the signal. So, here suppose this is a source. So, here the sensor will emit the light and then it will reach to the target and then the backscattered portion of the signal will be recorded here, right. The strength of the backscattering signal is measured to discriminate between different target and the time delay between the transmitted and reflected signal, which determines the distance to the target. Remember I told you that this is the microwave sensor which is illuminating this particular area, and here you have one small object, one tall object. So, which one will interact first? This taller one, and once it interacts, what happen? It will start sending the signal, right, and this will interact later and then this will also provide the information, right. So, this way we are having two information. The first one is time, how much time it took to travel. The second is the backscattering signal. So, now we will see what are the different advantages of microwave remote sensing. So, it has all weather capability because it can measure through the cloud cover, through the hazy atmosphere, and this has also day night ability because we also have active microwave sensors, right. So, this can also work in the night, but when we have the passive one, when we go for the passive microwave remote sensing, then here sun is our source of light. So, then we are restricted to do this microwave remote sensing only during the day. Penetration through a medium, because you have longer wavelength and the surface can be penetrated with this particular wavelength, that will be equal to your wavelength, right. Information through microwave is different from optical data, because here we are talking about the longer wavelength region, and in the longer wavelength region what happens? The back scattering is measured, right. The back scattering is not a superficial property, it is also having the subsurface information, right. So, this is not related to the composition. So, this is more because of the surface roughness, what is the geometry of the target. So, those things will control what is the moisture condition, that will control this back scattering signal, right. Information about the geometric properties of the various feature, that will be possible through microwave remote sensing, whereas in optical the geometric information is limited. Only when we go for the panchromatic image, we have the geometry of the target, right, because the spatial resolution is very high. When we talk about the penetration depth in the soil, you see the volumetric moisture content, when we have more moisture content, the depth of penetration will be less, right. When we are having the snow, here also you see volumetric liquid water content, and this is the penetration depth. So, when we talk about the less liquid water content, here the depth of penetration is high. When we have more volumetric liquid water content, the penetration is less. Similarly, penetration depth is high when moisture content is low. So, that means it is significantly influenced by the dielectric properties of the target. Now, referring back to the optical remote sensing, where we had the full domain starting from 400 to 16,000 nanometer optical remote sensing, which includes reflective plus emissive domain, right. Here we were not restricted to use a specific wavelength, only we have to check what is the atmospheric constituents, what are their different absorption positions. Based on that, we have to check the atmospheric window, and in those atmospheric window we can design a specific detector which is sensitive, maybe let us say 400 to 500 nanometer or 420 to 440 nanometer, right. So, we were free to use that, but when we talk about the microwave remote sensing, our bands are fixed, because here we are having more concern about the frequency, right. So, if you see here the band designation, so the K band, the first band, it is from 1.18 to 1.67 centimeter, right. Likewise, Ka, Ku, X, C, S, L, P band, and here according to their wavelength we have the frequencies, right. So, these are the fixed bands of microwave remote sensing. So, if you refer to any of the sensor which is operating in the microwave domain, they will define whether it is sensitive in C band, S band, L band or P band, right. So, here this is 30 to 100 centimeter, this is 15 to 30 centimeter, 7.5 to 15 centimeter. C is 3.8 to 7.5 centimeter. So, you will find most of the sensor working or operating in this particular wavelength, and corresponding to that you have the frequencies. Now, one thing that you will find this word at various places, which is called wave number. So, sometimes we define the wavelength in terms of meter, centimeter, right, micrometer or nanometer. But some of the papers or some of the books, they will be referring this wave number. So, what is wave number? Wave number is 1 by lambda. So, you do not get confused with wave number. If you have, you simply do that 1 by lambda, right, and then you can convert it to meter, centimeter, micrometer or nanometer. So, generally in physics people use more wave number, but in remote sensing when we talk about the wavelength, we generally refer to meter, centimeter, micrometer or nanometer, right. Now, there are two major types of radar. So, the first one is the pulse radar. The distance between the transmitted and the object can be measured. Speed can also be measured by constantly tracking the object, and that is change in the range from pulse to pulse, right. In the second one, which is the continuous wave radar, here we have Doppler radar and the frequency modulated continuous wave radar. So, FMCW, right. Police often uses continuous wave radar to measure the speed of cars. These are also being used for the aircraft altimeter, but these are not suitable for long distance range measurement. So, remember these are precise, right, and with that you can measure the speed of the car, and people are using it. In the traffic signal you will find many such cameras which are placed, and based on that only your speed will be calculated and people are charged penalty. And these are also used by the aircraft. So, their altimeter works with this continuous wave radar, and these are very precise. So, you will find at what altitude your aircraft is flying, right. A radar is essentially a ranging or distance measuring device, right. So, the main component of the radar system are transmitter, receiver, antenna and electronics to record the data, right. So, you see here this particular surface, right, which is illuminated by the microwave signal, right, and then back scattering is happening, and then it is going back to the space or in the atmosphere, and then your aircraft or the sensor which is attached to a spacecraft or aircraft, that will be measuring it, right. So, this is the basic principle of microwave remote sensing. Now, here if you see, the signals are sent, the house is interacting first with this signal. So, it will start sending the pulses first, right, and then it will be recorded here, and then what will happen? This signal which is recorded here, it will be stored, and then it will be sent to ground station when it comes in the proximity of the ground station, and then it will be circulated to the users, right. So, the back scattering is, you can say this is also a reflection, right, but only since we are talking about the longer wavelength, to discriminate it, the portion of the incident radar signal redirected directly back to the antenna through the target is known as back scatterer. So, here the target is known as backscatter and the energy is known as backscattering energy. So, here again referring to the basics of microwave remote sensing, the transmitter generates successive pulses of microwave pulses of A at regular interval which are focused by the antenna into beam B, right. So, here A is being sent successive pulses, the beam radar illuminates the surface at a right angle to the motion of the platform, right. So, this is the motion of the platform. The antenna receives a portion of the transmitted energy reflected or backscattered from various objects within the illuminated beam, that is C, right. Now, it is going back to the sensor. Subsequently, electronic system store this data in the form of two-dimensional image of the surface, because we have time and backscattering, right. And then subsequently it will be sent to the ground station and it will be distributed. Thank you. We will continue this with the second part in the next lecture. Thank you.